Let's talk about a strange and wonderful idea. It's about electricity. We use it for everything. It runs through wires in our walls, our phones, our cars, and in every single one of those wires we lose something. We lose energy. The wires get hot. That heat is the price we pay for moving electricity from one place to another. It's a tax, a law of nature, or so it seems. Your laptop gets warm on your lap. The power brick for your phone gets hot. The big transmission lines that stretch across the country lose a noticeable chunk of the power they carry just by bleeding it out as heat. It's friction, but for electricity. It's called resistance, but what if it didn't have to be that way? What if you could send electricity through a wire and have every single bit of it arrive at the other end? No heat, no waste, a perfect wire. That's not science fiction, it's real. It's called a superconductor. And the quest to make one that works in everyday conditions at room temperature is one of the biggest, most frustrating, and most exciting stories in science. So, could we build one? The honest answer is complicated. It's a story of incredible breakthroughs, crushing disappointments, and a puzzle that has stumped the smartest people on the planet for decades. To understand if we can get there, we first have to understand where we are now and how we got here. It all began over a century ago, in a lab in the Netherlands. A physicist named Heike Kamerlingh Onnes was obsessed with cold. He had figured out how to liquefy helium, a feat that got him closer to absolute zero than anyone had ever been before. Absolute zero is the coldest anything can possibly get. It's the point where all atomic motion is supposed to stop. Onnes was using his liquid helium to see what happened to materials at these extreme temperatures. He was curious about electrical resistance. The thinking at the time was that as you cooled a metal, its resistance would drop, but it would never go all the way to zero. There would always be some leftover resistance from impurities in the metal, so he took a wire made of pure mercury and started cooling it down. The resistance dropped, just as expected. Colder and colder he went, down to about 4.2 Kelvin. That's incredibly cold, just a few degrees above absolute zero. For reference, the coldest spot in outer space is about 2.7 Kelvin. So this was a truly alien environment, and then something impossible happened. The resistance just vanished. It didn't become very small, it became zero, gone. The instruments read nothing. Onnes thought his equipment was broken. He checked everything, ran the experiment again. The same result. The electricity flowed through the mercury wire without any friction at all. He had discovered superconductivity. This was a bizarre new state of matter. It wasn't just a perfect conductor. It did something else, something even weirder. A few years later, scientists discovered that when a material becomes a superconductor, it actively pushes magnetic fields out of its interior. This is called the Meissner effect, and it's why you see those famous videos of a little magnet levitating, floating in midair above a dark puck. That puck is a superconductor cooled to a frigid temperature. Its superconductivity creates a magnetic cushion that perfectly repels the magnet. It's not just a good wire, it's a material with almost magical magnetic properties. For decades, this was where things stood. Superconductivity was a laboratory curiosity. A fascinating piece of physics, but not very useful. The problem was the cold. To see this amazing effect, you had to use liquid helium. Liquid helium is expensive, difficult to produce, and a nightmare to handle. It boils away easily. Building anything practical meant building a machine that was essentially a super-powered, incredibly complex freezer. So, for a long time, the only real applications were for things that absolutely needed it, like the giant magnets and scientific experiments at places like CERN. It wasn't something you could put in your home or your car. The dream of a world run on superconductors seemed impossible. The big question was, why did things have to be so cold? A theory eventually came along called BCS theory, named after the three scientists who developed it, Bardeen, Cooper, and Schrieffer. It was a brilliant piece of work, and it won them a Nobel Prize. The theory is deep in the weeds of quantum mechanics, but the basic idea is this. Normally, electrons traveling through a wire are like people trying to run through a crowded hallway. They bump into the atoms of the wire and into each other. This bumping is resistance. But in a superconductor at very low temperatures, something changes. The vibrations of the atoms in the material, which normally cause chaos, actually start to help. An electron moves through, and it pulls the positively charged atomic nuclei toward it, creating a little ripple. A second electron a short distance away is attracted to this ripple. It's like one person walking on a soft mattress, creating a dip that a second person a few feet away rolls into. The two electrons, which should repel each other, end up linked together in a strange indirect dance. they form what's called a Cooper pair. These Cooper pairs are special, they behave differently, they move through the material in a coordinated, unified way, like a disciplined army marching in perfect step. They can move around the impurities and vibrations without being scattered. They flow without friction. They are a single quantum entity. This is superconductivity, but BCS theory also explained why it needed to be so cold. The glue holding these pairs together is very weak. Any amount of heat, which is just atomic vibration, would shake the pairs apart, and the material would go back to being a normal, resistive conductor. The theory seemed to put a cap on how warm a superconductor could ever be. It predicted that we would likely never see superconductivity above 30 or 40 Kelvin. It seemed the dream was dead. Then, in 1986, everything changed. Two scientists working for IBM in Zurich, George Bednorz and Carl Muller, decided to look where no one else was looking. Everyone was focused on metal alloys. These two decided to try a class of materials called ceramics. Ceramics are normally insulators. They're what you use to stop electricity from flowing. Think of a coffee mug. It was a crazy idea. They started cooking up strange new ceramic compounds, mixing different oxides together. And one day, they found it. A compound of barium, lanthanum, copper, and oxygen that became a superconductor at 35 Kelvin. This might not sound like much. It was still incredibly cold. But it was higher than the limit predicted by the old theory. It shattered the ceiling. It meant that something else was going on, that there was a new kind of superconductivity that the old theory couldn't explain. The discovery sent shockwaves through the physics community. Labs around the world dropped everything to start cooking their own ceramics. It was a frenzy. A few months later, a team in the US found another material, a compound with yttrium instead of lanthanum, that broke the next big barrier. It became a superconductor at 92 Kelvin. Why was 92 Kelvin such a big deal? Because it's warmer than 77 Kelvin. And 77 Kelvin is the boiling point of liquid nitrogen. Suddenly, the game had changed completely. Liquid helium was the expensive, difficult coolant. Liquid nitrogen, on the other hand, is cheap. It's abundant. You can make it by just cooling down the air we breathe. It costs about as much as milk. The dream was back on. Scientists called these new materials high-temperature superconductors, even though they were still far colder than a winter day in Antarctica. The excitement was immense. People talked about a new industrial revolution, maglev trains, perfectly efficient power grids, supercomputers on a desktop. It all seemed just around the corner. But then reality set in. These new materials were a pain to work with. They were ceramics, after all. They were brittle, like a dinner plate. You couldn't just draw them into a long, flexible wire like you can with copper. Making them into something useful was an enormous engineering challenge, and there was a bigger problem. Nobody knew how they worked. The old BCS theory was out. The electron pairs were clearly being formed by some other, much stronger glue, but no one could figure out what it was. For more than 30 years, this has remained one of the biggest unsolved mysteries in physics. We have these materials, we can use them for some things, like in MRI machines and some high-end power equipment, but we don't have the fundamental instruction manual. We're fumbling in the dark. The search for a room temperature superconductor continued, but it moved into a new and even more extreme direction. The focus shifted to the simplest element of all hydrogen. Theory predicted that if you could squeeze hydrogen with enough pressure, it would turn into a metal. And this metallic hydrogen should be a room temperature superconductor. The glue holding the electron pairs together would be incredibly strong because hydrogen atoms are so light and vibrate so fast. The problem? The pressure required is staggering. Millions of times the atmospheric pressure at the surface of the Earth. It's the kind of pressure you find at the center of a giant planet. Scientists can create these pressures in the lab, but only on a microscopic scale. They use something called a diamond anvil cell. They take two perfectly cut diamonds, the hardest material known, and use them to squeeze a tiny, tiny sample between their tips. Using this technique, physicists have reported creating metallic hydrogen. And they have found something else that's almost as good. Instead of pure hydrogen, they started mixing it with other elements to create compounds called hydrides. In the last decade, these hydrides have shattered all the temperature records. A compound of lanthanum and hydrogen was shown to be a superconductor at about 250 Kelvin. That's 23 degrees Celsius or 9 degrees Fahrenheit. It's the temperature of a very, very cold freezer. This was a monumental achievement. A superconductor working at a temperature you could find on Earth, albeit in Antarctica. But there was the catch. It only worked when it was being crushed under nearly 2 million atmospheres of pressure. Another group found a different compound, a mix of carbon, sulfur, and hydrogen, that seemed to superconduct at 287 Kelvin. That's about 14 Celsius or 57 Fahrenheit, a cool room temperature. For the first time, the room temperature part of the dream had been achieved in a lab. But again, it required mind-bending pressure. So we traded one impossible problem for another. We got rid of the need for extreme cold, but now we need extreme pressure. A wire that has to be squeezed between two diamonds isn't a wire you can use to power your city. It's a scientific curiosity, not a technology. The challenge now is to find a material that can maintain the superconducting state without the pressure. Can we create a chemical structure that mimics the effect of the pressure, locking the atoms into the right configuration? This is where the hunt is today. It's a search for what's called a metastable state. Like a diamond, which is just carbon that formed under high pressure but stays a diamond even when the pressure is gone. We need a superconductor that does the same. This long, difficult search is the backdrop for what happened in the summer of 2023. A team of scientists in South Korea uploaded a paper to the internet. They claimed to have done it. They claimed they had created a material, which they called LK99. That was a superconductor at room temperature and, crucially, at normal ambient pressure. No freezer, no diamond anvil, just a little gray-black rock that could change the world. The paper was not published in a major journal. It was just put online for anyone to see. And the internet went wild. The news spread like wildfire on social media, in forums, everywhere. Physicists, chemists, materials scientists, and amateur tinkerers all over the world rushed to their labs to try and replicate the recipe. The recipe itself sounded almost like kitchen chemistry. Mix some minerals, cook them in a furnace for a few days. It seemed almost too simple to be true. For a few weeks, the world held its breath. Videos appeared online showing a small flake of LK99 seemingly levitating, wobbling over a magnet. It wasn't the stable, locked-in levitation you see with cold superconductors, but it was something. Was this it? Had a small, relatively unknown team stumbled upon the biggest discovery of the century? The excitement was electric. People started dreaming out loud, a new era for humanity. The end of the energy crisis, flying cars, it was all on the table. But as more and more serious labs tried to make and test the material, the dream began to fall apart. The results that came in were inconsistent. Some saw a big drop in resistance, but not to zero. Others saw nothing at all. The levitation effect was explained away. It turned out that the material had complex magnetic properties, a mix of ferromagnetism and diamagnetism that could create a small repulsive force, making it look like it was levitating. But it wasn't the Meissner effect. It wasn't superconductivity. Finally, a couple of major research groups, including one at the Max Planck Institute in Germany, managed to create very pure single crystals of LK99. This was the definitive test, and their conclusion was clear. LK99 was not a superconductor. It was an interesting material, an insulator with some odd magnetic properties caused by copper impurities, but it wasn't the Holy Grail. The resistance dropped as it cooled, but it never came close to zero. The brief, chaotic global mania was over. The story of LK99 is a cautionary tale. It shows how much people want this to be true, but it also shows how science is supposed to work. An extraordinary claim was made. The community mobilized to test it. They shared their results openly and quickly. And in the end, the claim was shown to be false. It was a messy, public, and ultimately successful process of verification. It wasn't a failure, it was science doing its job, so where does that leave us? Yeah, we are still chasing the dream. The question of whether we could build a room temperature superconductor is really three questions. Is it possible according to the laws of physics? Is it possible with the materials we can create? And even if we find it, can we make it practical and affordable? The first question seems to be a yes. The work on hydrides under high pressure shows that the physics of superconductivity can work at room temperature. There doesn't appear to be a fundamental law that forbids it. The barrier is not a law of nature, it's a materials problem. The second question is the big unknown. Can we find a material that does what the hydrides do, but without the pressure? This is the core of the search. We are still largely guessing. Without a complete theory of high-temperature superconductivity, we can't just design the perfect material on a computer. It's still a process of trial and error, of mixing and baking, and hoping for a spark of something new. Scientists are using artificial intelligence and machine learning to sift through millions of possible chemical combinations, looking for promising candidates. But it's a search for a needle in a haystack the size of the universe. And the third question, about practicality, is just as hard. Let's imagine for a second that tomorrow a lab announces a credible, verifiable room temperature ambient pressure superconductor. Let's call it Miracle 8. The discovery is confirmed. Nobel Prizes are handed out. What happens next? The first thing is that Miracle 8 would have to be manufacturable. Can we make it in large quantities? Can we make it into long, flexible wires or stable thin films? The high temperature cuprates are brittle. What if Miracle 8 is just as difficult to work with? Or what if it's made of incredibly rare or toxic elements? The material itself is only the first step. Turning it into a technology is a massive engineering challenge. But if we could overcome all of that, what would the world look like? It's hard to overstate the change. The entire energy system would be rebuilt. Our power grid loses something like 5 to 10% of its electricity just in transmission and distribution. With superconducting wires, that loss would go to zero. You could generate power in the middle of a sunny desert or a windy plain and send it thousands of miles to a city with no waste. This would make renewable energy more viable and efficient overnight. It would fundamentally change the economics of power. Then there's energy storage. One of the big problems with renewables like solar and wind is that they are intermittent. The sun isn't always shining and the wind isn't always blowing. We need better batteries. Superconductors offer a solution called SMEs, or superconducting magnetic energy storage. You run a current through a big loop of superconducting wire. Once the current is in there, it will circle forever, with no loss. It's a perfect battery, storing energy in a magnetic field. With a room temperature superconductor, these could be built anywhere, stabilizing the grid and allowing us to rely completely on renewables. Transportation would be transformed. We already have maglev trains, which use powerful magnets to levitate and propel the train, eliminating friction with the tracks. But they rely on conventional electromagnets, or in some cases the older cold superconductors, making them very expensive and complex. With room temperature superconductors, you can make the magnets vastly more powerful and efficient. Maglev could become the standard for high-speed rail, connecting cities with silent, incredibly fast transport. Electronics would take a quantum leap. The heat generated by resistance is a fundamental limit on how small and fast we can make computer chips. A processor is a tiny city of billions of transistors, and the heat they produce is a major problem. That's why your computer has a fan and data centers need massive cooling systems. With superconducting components, you could build chips that are orders of magnitude faster and more powerful without generating waste heat. This would also be a huge boost for quantum computers, which often rely on superconducting circuits that must be kept near absolute zero. Medical technology would improve dramatically. MRI machines use powerful superconducting magnets to see inside the human body. They require liquid helium cooling, which makes them big, expensive, and loud. A room temperature superconductor would allow for smaller, cheaper, and more open MRI machines, making this life-saving diagnostic tool available to many more people. The list goes on and on. Electric motors in cars and airplanes could be made smaller, lighter, and almost perfectly efficient. Scientific instruments, from particle accelerators to telescopes, would become more powerful. It would be a genuine technological revolution on par with the discovery of electricity itself. So we're back to the original question. Could we build one? We are not there yet. We are not even close to having a practical device. We have clues. We have tantalizing hints from the world of high pressure. We have the lingering mystery of the cuprates. We have the cautionary tale of LK99. What we don't have is a clear path forward. It feels like we are in the 18th century, and someone has just shown us a tiny piece of metal that gets hot when you put it near a lightning strike. We know there's something called electricity, and we can see a faint glimmer of its power, but we have no idea how to build a motor or a light bulb or a power grid. That's where we are with room temperature superconductors. We've seen the effect in extreme conditions, but the gap between the lab discovery and a useful technology is immense. The search is one of the great remaining challenges in physics. It requires a deeper understanding of the quantum world than we currently possess. It requires a mastery of materials science that is still beyond our grasp. It might take another 50 years. It might take another century. It's even possible that a room temperature superconductor that is also cheap, strong, and easy to make is just not something the universe allows. Maybe the conditions required will always be too specific, too fragile for everyday use. But scientists will keep looking. The potential reward is too great to ignore. Every year, new materials are created and tested. New theories are proposed. The problem is so hard and the goal so profound that it will continue to attract brilliant and dedicated people. It is a slow, grinding process, punctuated by moments of thrilling discovery and crushing disappointment. So, For now, our wires will continue to get warm. We will keep paying the tax of resistance. But the dream of a perfect conductor, of a world without electrical waste, remains. It's a powerful motivator, and while we can't build one today, it is the hope and the dedicated work of thousands of scientists around the world that means one day we just might. It's not a certainty, but it is a possibility, and in science, sometimes a possibility is all you need.